Welcome. In this session, I will briefly describe the method of secant that help us to approximate the solution to the equation f of x equals to 0. The second method is actually derived from the structure of the Newton-Raphson method. So we know that the Newton-Raphson method is given by xn plus 1 equals to xn minus f of xn divided by f prime at xn. Let's call this one 1. Then let xn and xn minus 1 be given as two approximate roots to the equation f of x equals to 0. Then we have the points xn, let's call this point A, f of xn, and B, xn minus 1, and f of xn minus 1. On the graph of y equals to f of x. Now, we can approximate the derivative f prime of x by the expression f of xn minus f of xn minus 1 over xn minus xn minus 1, i.e. the gradient of the second line joining A and B. i.e. we'll say f prime of xn is approximately f of xn minus f of xn minus 1 divided by xn minus xn minus 1. So let's call this one 2. Now, this equation 1 that describes the Newton-Raphson method can be written as, so 1 may be written as f of xn equals to xn plus 1 minus xn into f prime of xn. This is what I'm doing. I'm simply taking xn to the opposite side, and then I rearrange this term f of xn, take it to opposite side, and then multiply through by f prime of xn. So we have negative. So which I can write this one as minus or positive f of xn. Dividing through by negative, I'll have this one now as xn minus xn plus 1 multiplied by f prime of xn. Call this one 3. Now using 2 in 3, this means that I rewrite this derivative of the function in terms of this difference quotient. We have f of xn is given by xn minus xn plus 1. I multiply this one by f of xn minus f of xn minus 1 divided by xn minus xn minus 1. So this is the f prime. So I multiply through by this quotient, and I have xn minus xn minus 1. I multiply by f of xn is equals to xn into f of xn minus f of xn minus 1, and then minus xn plus 1 into f of xn minus f of xn minus 1. So opening brackets here, I'll have xn, f of xn minus xn minus 1 times f of xn equals to xn times f of xn minus xn times f of xn minus 1. This one I don't have to open because I'm solving for xn plus 1. I just write minus xn plus 1 into f of xn minus f of xn minus 1. So you see, after doing this expansion, this term and this term cancels out, so that we have taking this to the left hand side, now I'll have positive sign. So I'll have f of xn minus f of xn minus 1, and then xn plus 1 equals 2. So I've taken this to the left hand side, so I take this one to the right hand side, and I'll have xn minus 1 f of xn minus xn f of xn minus 1. And because we are interested in getting the value of xn plus 1, I have divide through by f of xn minus f of xn minus 1. Then I do the same for this other side, f of xn minus f of xn minus 1. So to remain with xn plus 1 on the left hand side, I have to cross in this bracket and then this other bracket. So therefore, x n plus 1 will be given by x n minus 1 f of xn minus xn f of x n minus 1 divided by f of x n minus f of x n minus 1. So this is the second method for approximating the root of the equation f of x equals to 0. So this is the second method formula for approximating the root of the equation f of x equals to 0. Now let me call this formula star. So note to apply this star, we must have two initial approximations of the root, i.e. xn and xn minus 1 must be given. Now, sometimes the question will be, you'll be given, sometimes they will not give you. So note we find these two initial approximations to the root of f of x equals to 0 using any of the previously discussed methods. So either use bisection, Newton-Raphson, or the regular fault side method. So next session, we discuss an example on how to illustrate or how to apply the second method for root approximation. Thank you.